Hello everyone, this is Anxi. I'm a PhD student from HKUST. It's my pleasure to introduce our work as multi-choice search in connected collective graphs. Here is the outline, and I will start from the background and motivation. The graph is a concise structure consisting of vertices and edges and is divided in multiple fields. Community search is a popular topic of graph processing, which intends to find a specifically connected subgraph for the given query vertices. Community is a concept generated from social networks, while this not only works in social analysis but also applications like citation network and knowledge base, etc. The K-trust model has received considerable attention due to its strong structural cohesiveness and high computational efficiency. Specifically, K-trust is defined based on undirected triangles. By definition, every edge in a K-trust is contained in at least K-2 triangles. However, K-trust is unsuitable for directed graphs. This is because undirected graphs have only one type of triangles, while directed graphs could contain two types of triangles, that is, cycle triangle and flow triangle. A cycle triangle is a cyclic directed graph of three vertices. We can find a hub vertex in a flow triangle, where the other two vertices always point to it, while we cannot distinguish such a vertex out of three vertices, which are connected cyclically. For capturing asymmetric relationships between entities in directed graphs, the D-trust is proposed as a cohesive subgraph structure, which is defined based on two types of triangles in directed graphs. In a D-trust, or KC-KF trust, each edge is involved in cycle or flow triangles with at least KC or KF other vertices. Applying the K-trust in directed graphs by ignoring the directions of edges cannot distinguish these different triangle participations of each edge. The D-trust shows advantages in CS over directed graphs compared with the K-trust. The figure A shows an example of the social network. The direction of an edge represents the following relationship between two users. That is, the edge V1, V2 is that user V1 follows the user V2. Users always follow and unfollow others according to their interests, which will result in the update of the whole graph. In figure A, we mark all D-trusts in different colors in the original graph G, and in the graph B, that strategy B delete V1, V3, delete V3, V1, delete V2, V4, but add V5, V2. After applying strategy, the result of the trust search becomes different from the results in figure A. So considering directed graphs in the real world, they are always changing with edges or vertices being continuously to change from the original graph. Though the effective and efficient solutions for K-trust maintenance problem of both single update and batch update are developed, it is not trivial to extend the solutions to K-trust. The first is because different triangles in directed graphs can be classified into two types. And second, the K-trust ignore duplicated edges, while two edges with different directions are allowed between two vertices U and E. The theoretical hardness of the D-trust maintenance is unknown because of these 2 points. According to the two different types of triangles, the D-trust decomposition is naturally related to two types of supports. For single edge updates, existing work process proposes theorems that indicate the rules of the K-trust maintenance depending on the only type of the support. The fact that the same three vertices can be contained in multiple triangles in the D-trust makes such theorems cannot be extended practically. For more efficient batch update solutions, the existing index of K-trust stores edges in the non-ascending order of K values. However, there are a pair of values to consider KCKF for the D-trust. The dominant property of KCKF makes it impossible to construct such an index for the D-trust. Next, I will introduce our formal problem definition. The D-trust is proposed together with two types of support. The cycle support of the edge is the number of vertices that form cycle triangles with E in graph G. The flow support is defined similarly. The maximal D-trust requires the threshold and the maximality. The pair KF KC is called a trustness of E, where the KC is the cycle trust number and KF is the flow trust number. Consider a static graph. The problem of searching a maximal D-trust aims to find the subgraph satisfies contentment, connectivity, and maximality. However, the solution of MDS performs inefficiently when strategy is given because it has to recompute the result from scratch. We extend the problem of MDS to two advanced problems, considering the scenario of dynamic directed graphs. Given a directed graph G and a set of to be updated edges strategy, the problem of MDM is to compute new trustness set of any edges in the edge set of G O plus strategy, where the O plus means the changes are applied. We use G prime for short of G O plus strategy. Note that the solution of MDS forms inefficiently when strategy is given. So the solution of MDM is expected to handle strategy much more efficiently, which is the data update of MDS. What's more, the solution of MDSM shall then answer the new query by maintaining the old result, which is the query update of MDS. Next, I will formally introduce our basic single update algorithms. We consider the cases of single edge deletion and insertion for the MDM problem, since the single update is the most basic scenario of dynamic directed graphs. Before presenting the proposed algorithm, we introduce some typical operations of the support maintenance. To distinguish different connections between two vertices U and V in directed graphs, we say U and V are unilinked. If there exists an edge, either UV or VU, they are bilinked. If they exist both UV and VU, and they are not linked if there exists no edge between them. We observe that it is not necessary to recompute supports of affected edges, but it can be maintained by two proposed operators, ins and delay. Also, operators ins and delay can update supports efficiently for all edges that is incident to all vertices in NC G prime E star and F G prime E star with a time constant of O sigma. Z times degree of D only. The correctness is guaranteed by the lemma 5.1. And consider a single edge insertion U plus UV. It is known that U and V are unilinked before the inversion, and so for the updating of the cycle support and flow support, the cycle for increased by 1 or for any edges E, and the flow support increased by 1 for any edges of EF with a time constant of degree U plus degree V. And the main idea to maintain supports by operators first, then update those whose edges who can be directly judged according to the lemma. This is the main idea of the single edge deletion algorithm. So for the single edge inversion algorithm, the main idea is similar to the deletion, and we also have to initialize the variables first, and then we call operators to update supports. And after that, we maintain edges for those who can check immediately after applying operators. And after that, we may also check other edges that may be affected or not. Next, we present our efficient order-based index, which can perform batch updates. We present the index design first, and then illustrates its rationale for maintenance. We propose an order-based index called the D-index, which can perform batch updates. We present the index design first, and then illustrate its rationale for the maintenance. So for the definition of the cycle decomposition order is given like a sequence of edges in the subgraph H narrow KFI that follows the order of the decomposition along the cycle trust numbers. We denote it by the sequence KFI, and for any sequence KFI of G, it is divided into segments where edges within a segment share the same cycle trust number. We denote a segment by the SEG KCI KCJ KFI. And the existing index of the K-trust source edges in the ascending order of K values. But for the D-trust, it is possible to take the both of KCKF, this pair of value into the section or index. So this index to make the MDM problem harder for addressing the hardness, we design our index and batch update algorithms as follows. This index can be inherently constructed by the D-trust decomposition algorithm. Note that there may exist many valid CD orders for a single KFI, since all edges within the same segment can be peeled off in any orders during the process of the D-trust decomposition. We keep an arbitrary valid CD order for each FI in the index, and maintain these CD orders one by one for the MDM problem. We consider edge insertions. Within the segment KCJKFI, we mark edges whose trust will change into boxes, where the edges in box 1 will move to sec prime KC KFI, and the edges in box 2 will move to sec prime KC plus 1 KFI. Within sec KC KFI, we mark edges whose trustness remains same in box 3, and mark the edges that will move to sec prime KC plus I KFI in box 4, and we denote the edges set where each edge exists in the KCKF prime trust, but not in KCKF trust by nsec KCKF. In this way, we have nsec KCKFI equals to box 1 union box 2, and the segment KCKFI equals to box 3 union box 4. And segment prime equals to box 2 union box 4, and sec prime KFI equals to box 1 union box 3. We can regard all these unions as additions because each pair of boxes is disjoint. We naturally obtained that such relationships always holds for each CD order and itself after maintaining. We have such for all flow trust numbers KFI. In this chapter, we introduce our batch update algorithms based on the D-index. And the main idea of batch edge deletion algorithm is that we maintain orders by all three variables, RAM and TS. Here, these two variables are utilized in the way that the TS is defined as the number of cycle triangles where the other two edges, E prime and E prime, both have their cycle trust numbers no smaller than KC of E. And note that all existing trust needs sets are obtained from the old D index, and we update the flow trust number of edges that exist in the next city order by picking a tighter upper bound to squeeze the search space, and we update the E up and the necessary variables in line 20 and return the results by node. And for the batch edge insertion algorithm, we denote that batch to be inserted edges by E plus, and our batch edges initialize variables first, and YAP is initialized and maintained similarly with the batch deletion algorithm, and we update exists for edges after each start inclusively in squeeze KF, and then we propose edges according to 3 cases of different exist and remain mentioned before, and then we maintain that initialize the NSEC KC plus 1 KF. And after that, we squeeze the search space for the maintenance of each edge. We update the E up and necessary variables. And note that the O-ins and O-delete can be done in O1 based on the order maintenance algorithm. And based on the batch edges update algorithms above, we present a fully dynamic MDSM query algorithm. For the given batch updates, consists of batch edge insertion and deletion. We remove the insertion and deletion of the same edges first, and then move deletions in the first half of the updates, and leave the insertions in the second half of the updates. And the query performs like that. We consider all edges in the given query result before applying the edges updates, and find those whose trust needs can dominate or equal KC prime, KF prime, and mark them as capped. After inspecting trust needs, we check the connectivity, and also conduct searching based on edge by the index-based query algorithm. Finally, we check the containment of Q prime of the results community. In this chapter, we introduce our batch update algorithms, experimental evaluations. We conduct all experiments on a Linux machine with an X on Gold 6240 R CPU and 1000 GB memory, and we use 7 real-world data sets which are publicly accessible, including EM, TWPS, WK, and etc. We compare the baselines for listed clearly for MDM problem and MDSM problem respectively. And for all data sets, the index can be built within 2 times 10 to the power of 4 seconds, and the index size is within 85 GB. And we conduct experiment on investigating the impact of dirt G over EM and TW. And we can see that B-ins performs better than S-ins or UB-ins consistently, and the B-ins runs faster than the DAC with the dirt G of around 12% of EM and around 10% of TW. The second fact is that B delay also performs better than S delay or UB delay consistently, and the B delay is more efficient than DAC with dirt G of around the 20% for both data sets. And the third fact is that S-ins and S-del performs better than UB-ins and UB-del coordinatedly, which implies that the single update algorithms are more efficient than the index because of index relating process and costly than index-free operators under the single update setting. The impact of the size of G is evaluated on 2 largest datasets, PK and delay, with 3.6 million edges and 136.5 million edges respectively. And we can find that for edge insertions, B-ins and S-ins scale well and perform better than DAC as the size of G getting longer, but UB-ins is not always scalable, especially for very large datasets, since too many low-level operations are executed in UB-ins for each unit update, and the time cost of these operations gets longer when the size of G gets longer. For edge deletions, all algorithms performs well, and the delay performs best in the experiment, since all of them are bounded. And for varying the size of Q and the size of dirt Q and the KC and prime and KF prime, for varying the size of Q, when the size of Q gets larger, the re-query and co-query cost more time than maintain query and OP query, since the dominating cost of re-query and co-query is from the static decompositions from scratch. MT query and OP query show better scalability, and when the size of the Q varies from delay 3 to increase 3, the impact is similar to the size of Q. And because when the size of the Q gets larger, it needs to check more query vertices. And in all tested cases, co-query, MT query, and OP query are much more efficient than re-query. And OP query performs best among all competitors because OP query utilizes more previous results instead of the only the latest one. And for varying the KC prime and the KF prime, either KC prime or KF prime gets larger, all methods run faster because the size of the result gets smaller. OP query is the most efficient one among all competitors with the same reason above. And here's the summary. In this paper, we propose a collection of incremental solutions for maximal trust search in dynamic graphs, including single update algorithms and order-based index that can handle batch updates efficiently. We conduct a theoretical bounding analysis of the maximal trust given page insertions and deletions respectively. We further present a fully dynamic Turing algorithm to help accelerate the Turing processing. Extensive experimental results on real-world graphs validate the effectiveness and efficiency of our solutions. Thank you for listening.